So I do remember the first time I held a moon sample. It was in a course at undergraduate level.
I remember being in school and a scientist came and gave a talk, and he actually brought a lunar meteorite.
And at this point he put what we call a thin section, so we could look down the microscope at them. A thin section is actually a piece of rock that's been sliced, about the same thickness as a piece of hair. You can shine light through it and you can look at all the different minerals that are in the rock.
So they're actual meteorites that fall on Earth that are made of pieces of the moon. I remember holding this piece of a lunar meteorite. It was pretty small, and I remember thinking, wow, this is so small. We really need more of this. I remember that was my number one thought, was we need more of this. We need a lot more.
I went home and I think I rang every single person I knew. I definitely told my family a million times. I don't think they were sick of me, but like they were definitely go away and tell us something different now. But no, they weren't. They were over the moon as me. Pun intended. Yeah.
For the past 50 years and counting, generations of scientists like Dr. Natalie Curran have been probing rocks brought back by Apollo astronauts using increasingly sophisticated technologies. We've learned that our moon is so closely related to Earth that the two must have formed from some of the same material. Moon rocks showed the first evidence that the moon has water, and they've even helped in studying the history of the sun, which influenced the evolution of life.
I work in the Mid-Atlantic Noble Gas Research Lab, or MNGRL. You know, we're called Moon Girl Lab because we work with lunar samples, but it's actually a fun name because we're actually predominantly female scientists that work in there. We are looking at basically the history of lunar samples, and being in this lab, we're basically rock detectives. So we're looking at how old the sample is and what the sample's made of. The reason why we want to answer these questions is because they can tell us a lot about how not only this sample formed, but also how the moon formed, or what the geological processes are that are occurring on the surface of the moon.
So working with the Apollo samples, I honestly try to take the emotion out of my lab work. It's very humbling. It goes over my head, to have a piece of the moon in my hands. I study the origins of organic matter in space.
Organic matter is what makes up all life on Earth. Dr. Jose Aponte and his colleagues are trying to figure out how the chemical ingredients for life got to Earth, and whether they ended up on any other planets or moons. Although there was never life on the moon, it's an important place to study as a record of the events, such as asteroid collisions, that shaped the solar system. Rocks on the moon are better preserved and far older than any rocks we found on Earth.
My job is integrating science into human spaceflight. So how will we do science on the surface of other planets with astronauts? We like to say that the moon is a witness plate for the solar system, and it's really true. When you look at our planet here on Earth, you see, things that we all really like a lot, like vegetation and the oceans and, cities where people live. But all of these things combined with the fact that our planet is actually very active, just look at plate tectonics, which creates new crust, which destroys old crust. It's, again, what drives our planet and the evolution of our planet. These are all things that we're very appreciative of and see every day, but they're things that actually obscure the geologic record. When you go to the surface of the moon, however, you have 4+ billion years of history preserved on the surface of the moon. By looking at one rock, you can learn a lot, just by using your own two eyes to interrogate a rock and make descriptions about it. You can learn something about how that rock got there, how the landscape around you got there, and you can start to really make broad interpretations about the area around you just by looking at literally one rock. Then imagine taking that rock back to a lab, which you can use these really high resolution lab techniques that we have to peer inside the rock, get a look at what you can't see with the naked eye, start to understand how old that rock is, how long it's been sitting there on the surface.
So it's really exciting to think that this some small little sample can tell us a lot about different processes that are not just going on from the local region where this sample was picked up, but actually from the whole of the moon as well.
By studying just one rock, you can learn about potentially billions of years of solar system history. And so imagine the scientific discoveries that we made with the couple 100 pounds of rocks we brought back from the Apollo missions.
During 6 missions from 1969 to 1972, Apollo astronauts brought back 842 pounds of rocks, pebbles, sand, and dust from the moon. Today, those samples are carefully stored in a special facility at the Johnson Space Center in Houston. The same facility will store the rocks to be collected by Artemis astronauts.
So I work in what's called the Astromaterials Acquisition and Curation Office. We just call it the Curation Office for short. So all of the Apollo moon rocks, meteorites, all of our sample return missions from asteroids, from comets, all of those samples come here to Houston, and it's our office's job to take care of those samples and make sure that they're available to the scientific community to study.
The Apollo astronauts all landed near the moon's equator. Samples from there have been instrumental to science, but scientists want to explore other locations on the moon. Otherwise, it would be like landing in the Arizona desert on Earth, and assuming that the conditions discovered there reflect those found on the entire planet. Compared with Apollo, Artemis astronauts will carry out a very different mission in a drastically different environment. They will venture to the South Pole, a region that has water ice and could be rich in other resources. The South Pole is a land of extremes. Temperatures there can reach negative 400 degrees Fahrenheit.
I would actually even say curation starts as soon as the mission starts. So one of the things that I'm talking to the EVA engineers about a lot and the astronauts is how to prepare for when they're going to go to the moon. For example, we know that we're going to collect some rocks. What container are we going to put those rocks in? Are we going to put them in a can? Are we going to put them in a bag? And we need to understand that, because for some of these samples, they are very sensitive to whether they're exposed to metal or plastic. And those are design decisions that have to be made years before the mission even flies.
They've got to be super strict, the astronauts on the surface. But me, I'd be like, I'd be like a kid in a candy store and just want to, I want to take everything. And, you can only go a certain amount of time. I'd probably run out of oxygen, me. I'd be walking and forget.
It's often said that, exploration is part of human nature, and I definitely agree with that. I mean, even as a small kid, going out in my backyard and, picking up dirt and sticking my hands in the creek and understanding what the little animals and plants were all around me was something that, I didn't have taught to me by that age. It's just something that really comes naturally to, I think, most people. And the same is true on a much bigger scale. The desire to explore the solar system and learn more about, what we can look up in the night sky and see is really a fundamental part of human nature.
If we want to visit Mars, if we want to explore the solar system, or if we think about going to other planets, we first must learn how to operate on the moon.
Getting ready to conduct science on the moon and to identify scientifically interesting surface features takes a lot of practice. On the next NASA Explorers, Space School, how is NASA preparing astronauts to think and act like geologists?